Imagine you are strapped into the left seat of an Airbus A320.
Right.
You're lined up on the runway, the thrust levers are pushed forward, and you are accelerating past 130 knots. I mean, everything feels perfectly routine.
Just a normal day at the office.
Exactly. The engines are roaring, the runway centerline is just a blur, and you are literally seconds away from rotating into the sky.
Yeah.
But just off the departure end of the runway, completely invisible to the naked eye, there is this massive column of cold, dense air plummeting from the base of a thunderstorm.
Yeah, microburst.
Yes, a microburst. It slams into the earth, it violently curls outward in all directions, and if you fly into it, you are about to hit a sudden, massive headwind.
Which is then followed almost instantly by a crushing downdraft.
Right, and then a lethal tailwind that will basically attempt to physically strip your 70-ton aircraft of every ounce of its kinetic energy.
And that transition from the headwind to the tailwind, that is what makes this specific atmospheric phenomenon so incredibly deadly.
Because it's not just a bumpy ride.
No, not at all. It is not just turbulence. It's the atmosphere actively robbing the aircraft of the airflow it needs over the wings to stay in the sky.
Wow.
If you're, say, 50 feet off the ground when that tailwind hits, your airspeed drops instantly, your lift vanishes, and, well, gravity just takes over.
That is absolutely terrifying. So welcome to today's deep dive. We were taking you directly inside the A320 briefing room.
It's a great topic today.
Okay, let's unpack this because we're going to explore the precise, highly choreographed masterclass of how Airbus pilots actually manage this invisible killer.
Yeah, we're looking at the specific systems, the aerodynamics involved, and the really intense psychological friction that happens in the cockpit.
Because it's a fight for survival, right?
Wow.
Between a human pilot and a highly advanced flight computer in a low-energy, high-stakes environment.
It really is a masterclass in the human-machine interface, because surviving wind shear in an A320, it isn't just about raw flying skill.
Right.
And it certainly isn't about just throwing your hands up and letting the automation take over completely.
So it's a balance.
Exactly. It's about knowing exactly where the computer's logic ends and where the pilot's instinct must begin. This is the ultimate bridge between trusting computer automation and relying on raw flying.
So if we are going to fight this thing, I mean, the first step is actually knowing it's there.
Right. You can't fight what you can't see.
Right. A pilot cannot fight a completely invisible threat without sensors. And the A320 essentially has a dual-layer defense system to sense the air around it.
You have predictive wind shear, or PWS, and reactive wind shear.
Let's start with the predictive side. PWS is integrated directly into the aircraft's weather radar, right?
Yes, it activates automatically when you're below 1,500 feet on the radio altimeter.
But what I find so interesting is the mechanism here. Because it doesn't actually measure wind directly.
No, it doesn't.
It measures the Doppler shift of falling water droplets,
Mm.
which is kind of like, I don't know, echolocation for weather.
That's a great way to put it. The weather radar sends out these microwave pulses ahead of the aircraft, and those pulses bounce off precipitation.
Like rain or hail.
Yeah, rain, hail, even just really heavy moisture in the air. And because the radar can measure the frequency shift of those returning pulses, it can determine not just where the water is, but how fast it's moving.
How fast it's moving toward or away from the nose of the plane.
Exactly. So by mapping the velocity of those water droplets, the computer paints a highly accurate three-dimensional model of the invisible wind currents that are pushing that water around.
So it sees the wind by watching the rain.
Right. And it gives you a visual and an oral warning about conditions ahead of the aircraft, which gives you the chance to abort the takeoff or the approach before you ever enter the danger zone.
Okay, but relying on water droplets creates an obvious vulnerability, doesn't it?
It does.
Because what happens if you are flying out of a high-altitude desert airport like Phoenix or Denver, and you get a dry microburst?
Ah, yeah.
I mean, the air's sinking just as violently, but any rain evaporates long before it hits the ground. If the predictive system is looking for water droplets, what happens in a dry microburst? Does the plane just not see it coming?
What's fascinating here is that the system is entirely blind in that scenario.
Wait, entirely blind.
Completely. The radar pulses pass right through the sinking column of dry air, and the pilot gets absolutely no warning from the PWS.
Oh, wow.
And that specific vulnerability is exactly why the A320 has a secondary, completely independent safety net, the reactive wind shear system.
So if the predictive system fails because of a dry microburst, how does the reactive system catch it?
By entirely ignoring the world outside the aircraft.
Okay, so it doesn't look at the weather at all.
Not at all. The reactive system doesn't use the radar. It is a flight envelope function built directly into the flight augmentation computers, or the FACs.
The FACs, right?
Yeah. So instead of looking outward, it looks completely inward. It monitors the actual physical energy state of the A320 itself.
Because it's feeling the effects of the wind, not looking at the wind.
Exactly. The FACs are constantly running this incredibly complex equation, analyzing the aircraft's airspeed, ground speed, angle of attack, and the thrust being produced by the engines.
It's calculating whether the plane's energy is matching the performance it should be getting.
Precisely. If the engines are producing takeoff thrust, but the aircraft's energy is suddenly bleeding away in a manner that matches the specific aerodynamic profile of a wind shear encounter.
Bam! The alarm goes off.
Bam! The FACs trigger the alarm. You get a massive red wind shear warning on your primary flight display and a booming synthetic voice in the cockpit.
So the predictive system is designed to keep you out of the hazard.
Right.
But the reactive system tells you that you are currently inside it, and you need to fight your way out.
You're already in the fight.
Okay, so we have this brilliant dual-layer defense. But there's a massive catch to how these systems operate, specifically during the takeoff roll.
The inhibition logic.
Yes. The A320 utilizes a complex inhibition logic that actively suppresses these warnings at specific times.
It does.
For example, the predictive wind shear alerts are completely inhibited during the takeoff roll, from 100 knots all the way up until the aircraft reaches 50 feet of altitude. And the reactive system, it doesn't even wake up until liftoff.
That's correct.
So Airbus deliberately blinds the pilot to these alarms during the most critical, high-speed times of the runway run. Wait, the system deliberately turns off the alarm right as the plane is speeding down the runway. That sounds completely counterintuitive and terrifying.
It really does seem reckless until you understand the brutal physics of a high-speed rejected takeoff.
Okay, break that down for us.
Well, when you are heavy, accelerating past 130 knots, you possess an astronomical amount of kinetic energy.
Just massive momentum.
Right. If an alarm sounds and human instinct compels you to slam on the brakes to abort the takeoff, you are forcing the carbon brakes to absorb all of that energy in a matter of seconds.
Which creates a ton of heat.
Thousands of degrees of heat. The fuse plugs in the tires will literally melt to prevent the tires from exploding.
Oh my God.
Which means you are now rolling on deflated rubber at highway speeds. The risk of a high-speed runway excursion, meaning sliding entirely off the end of the pavement, becomes incredibly high.
So you are trading the possibility of a wind shear encounter for the certainty of a catastrophic braking event.
Exactly. And you also have to factor in the reality of radar technology. Predictive systems are highly advanced, but they're not flawless.
They can glitch.
They can be fooled by ground clutter, a dense flock of birds, a cluster of ground vehicles, or even strange radar reflections off airport hangars can occasionally trigger a spurious caution.
So you don't want to risk a deadly abort for a flock of birds.
Precisely. Imagine attempting a maximum energy-rejected takeoff, risking the aircraft and everyone on board because the radar briefly misidentified a flock of seagulls as a microburst.
Wow. Okay.
So Airbus removes the temptation entirely. Once you cross 100 knots, the safest place for you to handle a potential wind shear is actually in the air, using the aircraft's aerodynamic capability rather than trying to stop on the remaining runway.
But that creates a terrifying window of vulnerability. Because the computer is choosing to be silent to protect you from a false abort, there's a gap where neither system is going to warn you. You, the pilot, basically become the primary sensor.
We call that the observation gap. This is where airmanship takes over from automation.
So during this gap, before V1, which is the point of no return for taking off, the pilot has to actively scan the airspeed tape.
Right, you're looking for very specific clues.
You are looking for a sudden airspeed variation of 15 knots, or a vertical speed excursion of 500 feet per minute, or strange fluctuations in the autothrust.
Yes.
And if you see those specific physical indications on your instruments, you have to recognize the threat yourself and manually reject the takeoff.
But once you cross V1, that option is gone. You are completely committed to flying.
No turning back.
None. You rotate, the wheels leave the ground, and instantly that inhibition logic clears, the reactive system wakes up.
And starts looking at the energy state again.
Exactly. And this leads to a golden rule in Airbus philosophy. If that reactive red wind shear warning goes off after liftoff, you never second guess it.
You never assume it's a false alarm.
Never. Because it's not looking at radar bounces. It is measuring the fact that the aircraft's physical energy is dropping out from under you. You are in the fight.
Which brings us to the actual fight for energy. You are airborne, The wind shear hits, the tailwind shears your lift away, and that booming alarm sounds.
It's loud, too.
I bet. You are in a desperately low energy state, super close to the ground. How does the A320 automation actually help the pilot survive this low energy state?
Well, the primary defense mechanism is called alpha floor.
Alpha floor.
Yeah. When the shear robs the wing of its lift, the aircraft's angle of attack increases dramatically as the nose stays up, but the plane begins to sink.
Because it's falling.
Right. If that angle of attack hits a critical threshold, the flight computers instantly recognize that a stall is imminent.
And alpha floor activates.
Exactly.
It automatically commands TOGA thrust, takeoff, go around, maximum thrust, giving the engines the absolute maximum power they can physically produce.
But what is crucial to understand about alpha floor is that it is an absolute non-negotiable override.
Meaning the pilot doesn't have a say.
Basically, yeah. It does not matter where your hand is positioned on the thrust levers. You could literally have the thrust levers pulled back to idle, and the computer will still command the engines to spool up to absolute maximum power.
Oh, wow.
The system recognizes the catastrophic energy loss and just pushes the engines to their thermal limits to claw back every single knot of airspeed.
Okay, but raw thrust isn't enough to survive, right? I mean, if you have maximum power, but you pitch the nose too high, the wing airflow separates, and you stall anyway.
Right, you'll fall right out of the sky.
And if you pick too low, you just fly straight into the ground.
And that is exactly where the Speed Reference System, or SRS, takes over the flight directors.
SRS.
Yes. Once TOGA is triggered, the flight director bars on your primary display shift. They provide exact, mathematically perfect pitch guidance for the best possible climb performance.
So it's telling you exactly where to point the nose.
Yes. The flight computers calculate the absolute best possible aerodynamic climb profile for that specific turbulent slice of air. They command a pitch angle that extracts the maximum possible lift from the wing without crossing over the edge into a stall.
So your job is simply to put the nose exactly where the SRS commands.
Just follow the bars.
But surviving this low energy state also demands strict adherence to the aircraft's configuration, right?
Absolutely.
Because Airbus procedures strictly forbid pilots from changing the configuration of the plane during a wind shear encounter.
Yes, no changes allowed.
You cannot touch the flaps, and you absolutely cannot raise the landing gear until you are completely clear of the shear. Now, initially, that feels entirely backwards.
It does seem that way.
I mean, if you were struggling to climb away from the ground, wouldn't you want to pull the landing gear up to reduce drag and make the plane more aerodynamic?
It makes perfect sense intuitively until you look closely at the mechanical sequence of how heavy aircraft landing gear actually retracts.
What actually happens?
On the A320, the wheels don't just, instantly fold up into the fuselage. First, these massive hydraulic gear doors have to swing completely open downward into the slipstream.
Opening up the belly of the plane.
Exactly, creating this cavernous opening.
Moving the landing gear doors creates a massive amount of drag. It would be like trying to sprint against hurricane-force winds and deciding to pop open a large umbrella.
That is a perfect analogy. If we connect this to the bigger picture, you have to realize that for the 5 to 7 agonizing seconds it takes for those massive gear doors to cycle open, the aerodynamic drag on the airframe spikes massively.
Which you can't afford.
Not at all. In a wind shear encounter, your energy margin is razor thin. You are fighting for every single foot of altitude.
Right.
If you command the gear up, you are basically throwing out a massive aerodynamic parachute at the exact moment you need to be sprinting forward. Every drop of potential and kinetic energy must go into altitude, not fighting the drag of gear doors.
So you just leave the gear down.
You leave it down, you ride the drag you already have, and you let that TOGA thrust power you out of the danger zone.
This strict management of drag is also why there's a specific approach strategy for landing, isn't it?
Yes. It is.
Because if you suspect wind shear might be lurking near the runway on approach, the manual actually recommends selecting FLAPS3 instead of the normal full flaps.
It's a brilliant strategic compromise.
How so?
Well, full flaps give you the slowest, safest touchdown speed, but they hang far down into the slipstream, acting like massive air brakes. They create immense drag.
Right.
FLAPS3 provides slightly less lift, requiring a slightly faster approach speed, but it generates significantly less drag.
So you are basically optimizing your climb gradient capability in advance.
Exactly. If you hit the shear at, say, 200 feet and have to initiate an emergency go-around, you have fundamentally less aerodynamic resistance holding you back.
Because your engines don't have to fight the full deflection of the flaps.
Right, meaning more of that TOGA thrust translates directly into upward momentum. It also just gives the aircraft slightly crisper handling characteristics in the violent, choppy air you find inside a microburst.
Okay, so the alpha floor triggers maximum thrust, the SRS guides your pitch, and you keep your configuration locked. The automation effectively catches the airplane before it falls.
It does.
But escaping the wind shear is only half the battle, because once you fly out the other side into smooth air, escaping that automated rescue mode creates the biggest psychological trap for pilots in the simulator.
Oh, without a doubt, it is the ultimate psychological trap in the A320 cockpit.
Why is that?
Because once you are clear of the sinking air, you enter a completely different phase of the flight envelope. But the aircraft's brain is still locked in survival mode.
We're talking about TOGA, LK, TOGA lock.
Yes.
Because once the plane accelerates out of the dangerous angle of attack and exits the alpha floor condition, the flight mode annunciator, the FMA, displays TOGA LK. The threat is gone, but the thrust remains permanently locked at maximum. So what does this all mean? Why do highly trained pilots fall for this trap?
Well, imagine being the pilot in that scenario. You've just survived a terrifying low-altitude encounter. Your adrenaline is absolutely spiking.
Your heart is racing.
Exactly. And suddenly you hit smooth air and the aircraft is accelerating rapidly because your engines are still screaming at maximum takeoff power.
Right.
So human instinct takes over. When you're going too fast in a car, what do? You take your foot off the gas.
So the pilot instinctively grabs the thrust levers and physically pulls them back toward the idle position to slow down.
But the engines completely ignore the physical movement of the levers.
Wait, really?
Yeah. The levers are moving in the pilot's hand, pulling back, but the engine roar doesn't change. The aircraft continues to blast forward at maximum TOGA thrust, rapidly approaching its structural speed limits.
Why would Airbus engineer a system that ignores the physical inputs of the pilot? It seems like a recipe for a high-speed loss of control.
Because Airbus requires the pilot to prove they understand the state of the automation.
Prove they understand it.
Right. Alpha floor is a desperate life-saving measure. The computer took absolute control of the thrust to prevent a crash. When the immediate danger passes, the computer doesn't just hand control back automatically because it doesn't know if the pilot is fully aware of what just happened.
Oh, that makes sense.
It locks the thrust to ensure you don't accidentally stall the plane again. Pulling the levers back is an instinct. But disabling TOGA LK requires a deliberate cognitive action.
You can't just pull the levers. You have to manually disconnect the autothrust using the instinctive disconnect push buttons.
Exactly. You must press the buttons located on the sides of the thrust levers to completely disconnect the system, manually match the lever position to the engine output, and then re-engage the automation.
Wow.
It is the computer demanding a formal handshake. It forces you to read your FMA, recognize the TOGA LK mode, and execute a deliberate procedure to take your aircraft back.
That friction between raw human instinct, pulling a lever back to slow down, and the system logic perfectly highlights the final takeaway from the A320 briefing room. The golden rules of a wind shear encounter.
Yes, the golden rules.
When you're inside that microburst and the alarms are blaring, you have to strip away all the complexity and rely on 3 strict priorities.
Fly, navigate, communicate.
And they have to be executed in that exact order, right?
Exactly. The very first rule is to fly the aircraft. In a wind shear encounter, the pilot flying must aggressively follow the SRS pitch orders on the primary display.
Right.
And if the computer demands it, you pull your side stick fully back to the mechanical stop. You do not look down at your navigation display to see where you are geographically.
No navigating yet.
No, you stay entirely head up, entirely focused on your attitude and your airspeed.
But what if the automation fails you entirely? What if you hit the shear and those precise SRS flight director bars just disappear from your screen?
That is where the ultimate backup rule comes into play.
Which is?
You don't freeze, and you certainly don't waste time trying to troubleshoot the computers. You aggressively rotate the nose to an initial pitch of exactly 17.5 degrees.
Why 17.5 degrees specifically?
Because it is the absolute aerodynamic limit of the A320 wing. Engineers have calculated that at 17.5 degrees of pitch, the wing is generating the absolute maximum amount of lift possible without the airflow separating and inducing a high-speed stall.
Wow. So you are riding the razor's edge of the stall margin.
Squeezing every drop of performance out of the airfoil. It is the raw, instinctual backup when the silicon ships fail to give you a steering cue. You pitch to 17.5, and if the altitude is still dropping, you pull back even further, right up to the aerodynamic buffet, just to keep the plane out of the dirt.
It is a stunningly complex dance. Flying an A320 through Windshear isn't just about letting a computer do the work. It is a high-stakes, highly choreographed dance.
Absolutely.
It requires knowing exactly when to let the alpha floor automation save you and exactly when to assert manual control to disconnect a 2GA lock.
It demands total situational awareness. But, as we look at how pilots handle this in the A320, we have to consider where aviation is heading next.
Right.
The A320 is just one specific weight class with a very specific aerodynamic profile. But Airbus is currently rolling out the A321 XLR.
The new ultra-long-haul variant.
Yes, it is a significantly heavier aircraft with a totally different hybrid flap design.
So the physics are changing.
Exactly. The basic rules of aerodynamics remain the same, but the energy equations are entirely different. I mean, if you have a fundamentally heavier aircraft utilizing a different flap structure that changes the lift-to-drag ratio, how will that massive, heavy airframe handle the exact same loss of kinetic energy in a microburst?
Margins are going to be entirely different.
Exactly. Pilots are going to have to adapt their understanding of the aircraft's energy state to match a much heavier reality. It's a fascinating question for the future.
That is definitely something to ponder. So the next time you are sitting in the window seat watching the wing flex as you climb out of a stormy airport, just remember, you're not just riding in a metal tube.
Nope.
You are sitting inside a dynamic, flying supercomputer, constantly calculating the invisible energy of the atmosphere, ready to fight for every single knot of airspeed. Thank you for joining us in the briefing room today for this deep dive. Keep looking up, keep asking questions, and we will catch you next time.